This is a presentation for Splendor Project, and we are Team the Code Machines. So Splendor Project is a multiplayer card ball strategy game, and the goal is to maximize the points and get 15 points as soon as possible. And the agent can choose actions from collecting gems, reserve cards, buy cards, and the novel will visit automatically. And we'll also have a 1 second timeout limitation for each turn. We have implemented 2 methods, and we choose reinforcement learning as the final agent. Reinforcement learning allows us to try different actions and learn what actions give good rewards. We select Q-learning because it converges to the optimum policy and uses the best reward estimate instead of following the policy as SARSA. Additionally, Q-learning allows us to train the agent offline. Q-function approximation can reduce the table size, and it can calculate the Q value based on the sum of the features and their weights. The way of extracting features for each state, action pair, and weight will affect the performance for this method. We have included some basic features as the following for the first version, and we also include some advanced features. We consider about the importance if this action collects the useful gems, and so on, and we also consider about the opponent. We carefully design the rewards, and we give more rewards if this agent can gain more points or perform useful actions, and the reward area is the following. We have faced many challenges, such as more features and rewards did not always lead to better performance, and the training process is one of the biggest challenges we faced. After each modification, we need to retrain and gain a new weight, but sometimes long training iteration does not generate a better way to use. We need to do comparison and to select the best way to use. To gain a better performance, we need to deal with the balance between develop more features and rewards, and train the algorithm to get a good weight. For the further improvement, we will explore more useful features and rewards, and we will also investigate whether certain features can affect the performance of the agent. And we will also explore a better weight set. Then we will have a demo for the context between the first version of the Q-learning agent and the final version of the Q-learning agent. So agent 1 is the final version of the Q-learning agent, and we can see that blue cards are the most important to get because they appear in all the novels. Agent 1 buys a lot of blue, green, and white cards. Agent 1 also tries to get card that is both useful for novel visit and has points. However, Agent 0 has not bought any blue cards. Agent 0 also reserves a lot of unnecessary cards, and Agent 1 avoids these actions. Additionally, after Agent 1 has enough cards to buy other cards, it will not collect gems anymore.
Next, we will introduce our second method, Monte Carlo tree search algorithm. MCTS is a very popular method in game theory. As we know, the famous application of AlphaGo employed MCTS as its basic strategy to beat Lee Sedol. It has huge potentials in future extension. We will introduce our methods and functions used in 4 main processes. In selection, we employed 3 methods to select and try to prune the wasteful nodes. The first one is epsilon greedy. The second one is UCT. Note that we have to initialize all possible child nodes with Q value first. The last one combined UCT with other policy-based heuristics to prune the tree. In expansion, we employed simple policy-based rules combined with Q-learning to prune the nodes candidates and expand. In simulation, a simple way to simulate is to ignore the opponent agent in each simulation round. We also used policy-based agents plus Q-learning for both sides in simulation. For reward function, we spend a lot of energy in parameter tuning, which includes the reward setting for our actions and forestalling actions to prevent opponent feasible actions. In back propagation, we used Bellman equation to update each node in the simulation rows backwards. There were many challenges in developing. In selection, we have to develop better rules to exclude useless actions in the first place in order to reduce time consumption. We have to figure out more accurate and efficient game agents. For reward function, we made specific parameters tuning again and again to fit different game states. And the most critical one is the time limitation. We've tried our best to make MCTS iterate more times as much as possible, but still it needs a lot of improvements in the future. If we could have more time, we would add the pruning rules in the selection to reduce time consuming. We would also try different existing agents in simulation process to make it more efficient and quicker, and we will adjust the terminated state in simulation. Instead of setting certain depths, using heuristics to indicate the end of simulation could save a lot of time. This is a demo of Q-learning agent versus MCTS agent. In the mid stage of this game, we can see that Q-learning concentrates on noble card, while MCTS also aims at the high points card and store the black cards, which seems to be useless for getting noble cards. Overall, it is better than Q-learning agent. In conclusion, we choose Q-learning for the final contest, because MCTS still have the time exceeding issue that might bring uncertainty to the test, and the noise still exists which may decrease our performance of the learning agents in certain status. Thank you for your attention.